All right, so far in this test review, we've been determining whether a table is linear, quadratic, or exponential. We looked at equations to figure out whether they're linear, quadratic, or exponential. And now we're actually looking at patterns to determine how to find the explicit formula. And we're going to have to determine whether these patterns are linear or quadratic. I don't think any of these patterns will be exponential, but we'll see. So take a look at the pattern for 27. Now, this question has three parts: complete the table, write the formula, and graph. So let's take a look at completing the table first. So completing the table, let's figure out how many tiles we have in each one of these. We have 3 in figure 1. There's 2, 4, 6, 8. There's 10 in figure 2. And there's 1, 2, 3 times 1, 2, 3, 4, 5, 6, 7. We got 21 in figure 3. So you've got 3, 10, and 21. Now, interesting, on this table, it actually asks you for the next 2. And we can actually predict those based on what we see happening in the pattern. Let's take a look at our first and second difference. So our first difference here is from 3 to 10, we add 7. And from 10 to 21, we add 11. Clearly, that's not a linear pattern. So it must be quadratic because, like I said, we're not going to do exponential on these. So at least I don't think they do. So we'll look at the change here. And from 7 to 11, our second difference is plus 4. And because of that, we're going to add 4 to all the other ones too. Let me change that to a different color so you see this. If we add 4 here, and by the way, if we were checking exponential, you would see 10 divided by 3 is a fraction and 21 divided by 10 is a different fraction. So there's no common ratio or common multiplier. So then we know that the second difference has to be the same on every one if this is quadratic. So now we can actually figure this out. 11 plus 4 is 15. 15 plus 4 is 19. And now we can actually find the number of squares in figures 4 and 5. 21 plus 15 is 36. And 36 plus 19 is 55. So we can figure out the table just by looking at the first and second difference. Now the question is, what is the explicit function? And we've been doing this with tables, but class, we can actually use the diagram to figure this out as well. If we look at this, one of the things we talked about with patterns, especially with quadratic, is looking for squares, the biggest squares that we can find. Now, there's more than one way to do this. I'm going to show a particular way. You can look for squares. You can also look for rectangles. So let's take a look at squares. I like using squares better if I can. And I will go to figure 3 first. And if you take a look at this, this is 3 high. You can actually highlight this one right here. There's a 3 by 3 square. And here's another one, a 3 by 3 square. So let's do that one first. So remember, class, we talk about this. When we see a figure number, we typically represent that with the variable n. So in figure 1, n equals 1. Figure 2, n equals 2. Figure 3, n equals 3. And if you look at the size of this square is an n by n square. So I'm going to see if I can write over top of this. This is n squared. You know what? Can I make that a little bit darker? Let's see. Maybe I can write in white. Here we go. Let's take a look. No, white's not going to work. Let's try black. N squared. N times n is n squared. This is also 3 times 3, and that's n squared. Well, that works out kind of nice. And then if we look at the leftovers, well, what's left over here? We got this part here that's left over. I'll pick a different color for that. You can kind of see, class, well, that's also n. So that's just n squares. It's kind of cool. Let's see if that pattern works for the other two. So here we go. We'll use our blue. Here is a 2 by 2 squared. Here's a 2 by 2 squared. That one's also n times n, because n is equal to 2. So this is n squared. This is n squared. And then over here, we got our leftover, and turns out again, that's actually just n, or 2. 2 squared. So 2 times 2 is 4, 4, 4, and 2. Then, because I did the first one, it makes it easier to do the ones before that. So then this one is now, there's a square. There is a square. I'll write that above it. This is actually also n squared. 1 times 1 is 1. There's n squared. And here is our leftover, which just turned out to be the value of n. So we're using n to figure out a constant or a pattern that fits every one of these. Using the value of n, we can then say, okay, if n is 3, this is 3 by 3 plus 3 by 3 plus 3. N is 2, 2 by 2, 2 by 2, and then 2. So let's go to our explicit function. I'm going to write this as, we can just use f of x. I guess it doesn't matter what we use for our function name. Let's do f of n because we're using n. So f of n equals, well, if you look at this, I've got n squared plus n squared plus n. And these two terms are like terms. So here comes our equation. F of n equals 2n squared plus n. There we go. Now you could use rectangles as well, class. In fact, you could have just looked at the whole thing as a rectangle. This is a 3 by 7 rectangle. Well, the 3 is n, so the height would be n. The width is a little bit more work. You have to go from 3 to 5 to 7. Well, that's just a linear pattern. It'd be 2n plus 1. And if you multiply those together, you get the exact same equation. I think squares is usually the easier way to do it. And then the last one, class, is how do I graph this? Well, let's take a look. For figure number 1, you've got 3. Well, this goes by 5s, so this means this is 5 up. So we're going to go about 3 right here. And then at 2, we've got 10. At 3, we've got 21, so just above 20. At 4, we've got 36. Well, that goes off the graph, so we won't worry about that. So there's our graph. In class, since this is a pattern, it doesn't mean that it is continuous. We're going to treat it as discrete. Every one of these figure numbers has a specific number of squares, and there's nothing in between. There's no figure 1.5 or 2.7. So this is a discrete function. Your graph is done.